Every year, the world produces more than 110 million tons of fiber. A staggering figure, so vast that if all of it were joined into a single strand, it could wrap around the Earth over 3 million times. But what's truly remarkable isn't just the volume, it's how humanity has transformed these nearly invisible filaments into a trillion-dollar industry, quietly embedded in the most familiar things around us. From the clothes you wear every day, to packaging, and countless everyday items we often take for granted. Today, join Agriculture Insight as we explore the journey of these seemingly simple materials, where agriculture, science, and technology intertwine to create a vast network of fibers that is shaping life across the entire planet. A little-known fact: most clothing in the world is not made from natural fibers, but from plastic, primarily polyester, which accounts for about 70% of the global market. More strikingly, the raw material for this fiber often begins as discarded plastic bottles. Before being transformed into fabric, plastic must pass through the sorting stage, a critical step that determines the overall quality of the output. Although there are theoretically 7 recycling codes, in practice only PET and HDPE are clean and valuable enough to be reprocessed. In modern facilities, rotating drums, screening systems, and optical sorting robots work together to remove dirt and impurities, accurately separating materials with high efficiency. The selected plastic bottles are then shredded into small flakes, thoroughly washed, and processed through float sink separation to eliminate unsuitable materials. These flakes are melted, filtered through ultrafine screens, and cut into millions of plastic pellets per hour, an intermediate raw material used across various industries. From here, the pellets are reheated and extruded through spinnerets with microscopic holes, forming filaments finer than human hair. These fibers are rapidly cooled, stretched to enhance strength, and wound into yarn, serving as the foundation for polyester fabrics found in clothing, backpacks, and countless consumer products. The entire process represents a remarkable transformation, turning plastic waste into high-value textile material. However, its downside is becoming increasingly evident. During use, especially when washed, polyester fabrics release microscopic plastic particles into wastewater, which eventually flow into rivers and oceans and ultimately return to the human food chain, raising significant concerns about the true sustainability of the industry. Considered one of the rarest textiles in the world, Lotus silk is not only astonishing for its price, up to $2,000 for a single lightweight scarf, but also for the extraordinary way it is made. During the lotus season, stems are harvested directly from cultivated fields and natural ponds, then thoroughly washed and left to dry. The stems are carefully sorted into leaf stalks, flower stalks, and seed pod stalks to facilitate fiber extraction, spinning, and weaving. Before extraction, each stem must be cleaned meticulously. During the process, the fibers are often wiped with clean water to preserve their natural pale color. To produce lotus fiber, artisans delicately cut each stem, then swiftly pull, twist, and join the fine filaments into continuous threads. These fibers are extremely thin and soft, requiring exceptional hand skill. Each strand must be drawn and connected seamlessly as the process continues. A skilled worker can handle around 260 to 280 stems per day, yielding approximately 150 to 170 meters of thread. Notably, every stage is performed entirely by hand, with fiber extraction being the most critical step. Once extracted, the fibers are wound onto spools and spun to increase strength before being transferred to a loom, where thousands of fine threads are woven together into finished fabric. The final product carries a subtle herbal fragrance, combining the softness of silk with the breathability of linen. What truly sets Lotus silk apart is not just its high price, but the fact that behind each delicate piece lies hundreds of lotus stems and countless hours of meticulous craftsmanship. Did you know that one of the best insulating materials on the planet doesn't come from a laboratory or a high-tech factory? It comes from the nest of a sea duck, capable of retaining warmth in temperatures as low as -40 degrees Celsius. It's so rare that a blanket made from it can cost as much as a Toyota Camry. But what truly makes this material remarkable isn't just its thermal performance, it's the almost unimaginable journey required to obtain it. During each breeding season, female eider ducks pluck the softest down from their own bodies to line their nests and protect their eggs. Once the birds leave, collectors search for these nearly invisible nests hidden among grass, rocks, and seaweed. Each nest yields only about 15 grams of down, so light that even a sea breeze can carry it away. And that's only the beginning. What's collected is mostly a mixture of twigs, seaweed, and coarse feathers. Hours of painstaking work follow, as each strand of down is hand-picked, sorted, and meticulously cleaned. The clusters are then fluffed to assess cleanliness, loft, and down content. Once they meet the standard, they are carefully filled into small compartments within high-density cotton shells. Remarkably, just 1 kilogram of this down can contain over 1 million fine filaments, and a single nest is enough to begin the creation of one of the most naturally efficient insulating materials in the world. Over 5,000 years ago, while the pyramids were still under construction, humans had already learned to weave fabric from plant stems. That fabric was linen, one of the oldest textiles ever used, famously wrapping the bodies of Egyptian pharaohs. As summer reaches its peak in June, flax fields enter the most critical stage of their growth cycle, the harvest. Specialized machines move straight into the fields, where gripping mechanisms seize each row of flax and pull the plants directly from the soil. The stalks are immediately transferred onto conveyor systems, aligned in parallel, and spread evenly across the field in neat rows to dry naturally, while the seed heads are separated through suction systems. Within minutes, the entire field appears reprogrammed into orderly lines, marking the beginning of one of the world's oldest textile processes. After 2 to 4 weeks of field drying, when moisture levels drop to the ideal range, the flax is collected and transported to the factory. There, mechanical processing begins with continuously rotating rollers that break the tough outer layer. Next, high-speed scutching systems, operating at thousands of darbs per minute, remove nearly all of the woody core, leaving behind only the valuable long fibers. These fibers then pass through combing stages with hundreds of steel pins, aligning them, removing impurities, and sorting them by length, an essential factor that determines the fineness of the final fabric. Finally, the fibers are spun into yarn and fed into high-speed looms, where tens of thousands of warp and weft threads interlace with precision to create linen, a fabric known for its exceptional durability, natural breathability, and, despite having a coarser surface than cotton, a lifespan that can be up to 5 times longer under real-world conditions. At the next stop, we arrive at vast fields of white cotton, where not only soft fabrics are created, but also a key component of US dollar bills, turning an agricultural material into part of the physical foundation of currency. From the field, the entire process operates like a massive industrial system. Round module harvesters move continuously, using rotating drums fitted with metal spindles to carefully separate cotton fibers from plants standing 1 to 1.2 meters tall without damaging them. The cotton is immediately suctioned into the machine, transferred to a rear chamber, and compressed directly into cylindrical modules about 2.5 meters in diameter, each weighing up to 2 tons. Right in the field, every module is wrapped to protect it from moisture, effectively transforming the entire field into a closed-loop production system from the moment of harvest. After harvesting, Raw cotton is compacted into bales and transported to spinning mills, where this natural material enters a precise industrial processing chain. Once the bales are opened, high-speed rotating drums combined with strong airflow fluff the fibers, remove dust, and blend them for uniformity. The cleaned cotton then passes through carding machines equipped with hundreds of steel pins, aligning the fibers into a continuous sliver. These slivers are stretched, layered, and stabilized before being lightly twisted into roving. In the final stage, spinning frames operating at around 20,000 RPM draw and tightly twist the fibers into finished cotton yarn, ready for weaving. From a seemingly simple crop, cotton has become a global fiber source, accounting for about 25% of total production. Yet behind its widespread use lies a significant cost. A single t-shirt can require up to 2,700 liters of water, and although cotton occupies only 2.5% of agricultural land, it consumes nearly 16% of the world's pesticides, highlighting a major paradox of the modern textile industry. Once discarded in fields after harvest, few would expect that inside sharp pineapple leaves lie ultra-fine, nearly invisible fibers, delicate enough to be woven into piña fabric, one of the most valuable traditional textiles, priced at up to $300 per meter. When pineapples are harvested for global consumption, the long, spiky leaves are typically left behind as agricultural waste. However, for many farmers, these leaves are a valuable raw material for producing piña fabric. The leaves are cut using specialized knives, then fed into decortication machines to remove the fleshy layer and expose fine cellulose fibers running along the veins. These fibers are washed multiple times to eliminate sap, then sun-dried for 2-3 days until they become dry, lightweight, and naturally lustrous. Once stabilized, the fibers are combed straight, sorted by length and fineness, and twisted into threads before being transferred to a loom. There, warp and weft threads are carefully interwoven to create a fabric known for its exceptional lightness and breathability. Notably, producing just 1 meter of piña fabric requires around 80 pineapple leaves, and high-end handcrafted pieces can take over a month of meticulous labor, transforming agricultural waste into one of the most refined textiles in the world. First, we move straight into the beating heart of the circular economy, where household waste is no longer buried in landfills but reborn as biological fertilizer. From anonymous trash bags, an industry worth over $60 billion a year is emerging, turning environmental burden into sustainable revenue and new life for the planet. To turn waste into money, the first step is not technology, but separation. Fruit peels, leftover food, paper, and leaves are sorted out to be composted or recycled. In contrast, metals, plastics, and non-biodegradable materials are collected separately to prevent contamination, clearing the way for the real value hidden in waste. After preliminary sorting, tens of tons of household waste are transported each day to processing plants, where they officially enter the most critical stage of their regeneration journey. Here, waste is no longer a chaotic mix of debris, but a raw input for a tightly controlled industrial process. First, the sorted waste is conveyed onto industrial belts and fed directly into high-capacity shredding systems. Inside the crushing chamber, alloy steel blades rotate at high speed, powerful enough to break down bones, hard shells, and even the toughest organic materials. This process reduces the waste into uniformly sized particles, increasing surface area and creating ideal conditions for microbial activity in later stages. More importantly, shredding reduces waste volume by up to 40%, saving storage space and significantly lowering transportation costs. A modern industrial shredder can process between 10 and 20 tons of waste per hour, equivalent to the combined output of 1,000 manual laborers. Once shredded and homogenized, the organic waste mixture is sent directly to the composting area, where it is formed into long windrows or transferred into enclosed composting tunnels. Here, the life-critical process of organic fertilizer truly begins. Native microorganisms are rapidly activated, penetrating every particle and breaking down organic matter in a controlled biological process. Driven by intense microbial activity, the temperature of the compost mass gradually rises and stabilizes between 55 and 65 degrees Celsius. This temperature range is high enough to eliminate most pathogens, harmful bacteria, and completely destroy any remaining weed seeds. At the same time, turning and moisture spraying systems are operated regularly to maintain optimal oxygen levels and humidity. Through this process, what was once a chaotic pile of waste transforms into a closed biological system, cleaner, safer, and ready to move into the maturation stage of high-quality organic compost. After the active decomposition phase, the compost is transferred to a curing and biological stabilization stage, where its final quality is shaped. Beneficial microorganisms continue working quietly, completing the transformation of organic matter into stable humus. After the curing stage, the compost is screened to define its final value. The humus stream passes through rotary screening systems, separating material that meets the size standard of under 15 millimeters, accounting for up to 80% of the total mass, while coarser fractions are recirculated for further processing. As a result, the organic fertilizer achieves high uniformity, stable moisture levels below 25%, and is free of contaminants, ready for packaging. From raw waste at the start, the final product becomes a standardized agricultural input that can be applied directly to the fields. After leaving the screening line, compost is not yet released to the market. It must first pass through the final checkpoint, the QC lab. Here, samples are carefully analyzed for biological stability, including moisture, pH, and potential risks from heavy metals or residual pathogens. Only when all indicators meet regulatory standards, with moisture maintained around 50 to 60%, is the compost approved for use. This final control step eliminates risks at the last stage, ensuring a safe and consistent product. Once certified, the compost moves directly to the packaging line, where each bag completes its regeneration journey, ready to return to the fields as new agricultural value. Organic waste treatment reduces the amount of waste sent to landfills by 40 to 60%, easing pressure on the environment and urban systems. The resulting compost not only supplies nutrients, but also improves soil structure, enhances water retention, reduces nutrient runoff, and lowers dependence on chemical fertilizers. When properly regenerated, household waste is no longer a burden, but a circular resource that nourishes sustainable agriculture. More than 1/3 of the world's freshwater supply is used for irrigation, while clean water sources are becoming increasingly scarce and pollution continues to spread. Faced with this paradox, humanity has found a new path, transforming dirty water into irrigation water, regenerating the flow of life from what was once considered hopeless. To turn thousands of tons of foul-smelling wastewater generated every day into water safe enough for irrigation and the environment, the initial treatment process serves as a critical line of defense. As wastewater silently flows through underground pipes into treatment plants, it carries not only contaminated water, but also diapers, wet wipes, plastics, and fabrics. This is why public restrooms are forced to post warnings not to dispose of paper or waste into toilets. Each year, careless flushing habits generate hundreds of tons of non-biodegradable debris, enough to cripple wastewater treatment systems worth millions of dollars. Water that passes this first control stage then flows into grit chambers, where the flow is deliberately slowed, allowing heavy materials such as soil, sand, and stones to settle at the bottom. After coarse waste is removed, the wastewater enters a critical screening stage in the grit chamber. Flow velocity is tightly controlled and combined with precisely regulated aeration to trigger natural separation. Heavy particles such as soil, sand, and gravel quickly settle to the bottom, while the lighter water continues downstream. Each week, the system can collect and treat nearly 1 ton of inorganic grit, preventing damage to equipment in subsequent stages. From here, the wastewater flows into the primary settling tank, where gravity becomes the primary filter. After approximately 5 to 6 hours, most of the heavy sludge settles at the bottom, while clarified water separates above. Automated scrapers continuously remove settled sludge and floating scum, transferring them to digestion tanks. Through this step alone, more than 50% of suspended solids are removed, creating a stable foundation for the biological treatment and reuse stages that follow. From the settling tank, the wastewater enters the aeration basin, the living heart of the entire treatment system. Here, every cubic meter of water contains hundreds of millions of microorganisms working continuously in an oxygen-rich environment, created by constantly rotating aerators that keep the water in motion. These microbes convert waste into energy for the cleaning process. Within just a few hours, toxic ammonia and most organic compounds are broken down directly in the flowing water. No longer a matter of passive filtering or settling, the aeration basin functions as a precisely controlled artificial ecosystem, where more than half of the plant's overall treatment efficiency is determined before the water moves on to its final stage. Depending on discharge standards, the water continues through multiple cycles of biological treatment, including aeration and settling. After 18 to 24 hours, the flow enters a chlorine contact tank to eliminate pathogens, before leaving the plant and returning to the environment. Treating wastewater into clean water for agriculture reduces pressure on increasingly scarce freshwater resources, while transforming urban waste into a reusable resource. Treated water not only ensures reliable irrigation, but also helps maintain soil moisture under harsh climate conditions. When quality is strictly controlled, reused water limits environmental pollution, reduces discharges into rivers and lakes, and supports sustainable, circular agricultural production. Once burned or buried in oblivion, sugarcane bagasse and coconut husks are now rising as the black gold of the green era. More than 500 million tons of agricultural residues each year are being regenerated into biochar, a strategic carbon material for soils and the climate. From piles of ash, a billion-dollar market is emerging, offering a bold solution to soil degradation and the global carbon crisis. The biochar production process begins by fully harnessing 2 of the most abundant agricultural residues, sugarcane bagasse and coconut husks. At sugar mills, immediately after the juice is fully extracted, sugarcane bagasse is collected and stacked into mounds as high as hills. Under sun and wind, moisture gradually evaporates, leaving behind a resilient cellulose framework, the backbone of biogenic carbon. Once optimal moisture levels are reached, the bagasse is fed into fine grinding systems. Steel gears rotate continuously, cutting, tearing, and breaking down coarse fibers into a smooth, uniform material stream. Each grinder processes around 500 kilograms of dry bagasse per hour, ensuring a steady feed for the pyrolysis stage. A particle size below 5 millimeters not only allows for even heat transfer inside oxygen-free reactors, but also determines the porous structure, the very soul of biochar. At that moment, sugarcane bagasse officially sheds its identity as waste, becoming a strategic input for the carbon materials of the future. At the same time, another equally important supplementary feedstock, coconut husks, is collected from food processing facilities. In the past, more than 70% of coconut husks were discarded as waste, piled into massive heaps that consumed land and caused pollution. Today, that burden has been transformed into a resource. After being sun-dried to reduce moisture content below 20%, the husks are fed into vertical shaft grinding systems, where high-speed steel blades continuously cut, tear, and loosen their coarse structure. Within minutes, the tough outer shells are converted into a light, fibrous mixture, an ideal material for the pyrolysis process. After fine grinding, the mixture of sugarcane bagasse and coconut fiber is fed into a screw press, where a slowly rotating steel shaft generates immense compression, compacting the biomass and forcing it through a forming die. This process produces high-density biomass briquettes or pellets with a uniform structure. By being tightly compressed, the material achieves more efficient heat transfer inside the pyrolysis reactor, while gas flow remains stable and controlled. As a result, the biochar forms with fewer fractures and a more consistent overall quality. Incense is an ancient tradition of Asia, yet the strongest growth momentum of this industry is now coming from North America and Europe, where incense has become a familiar part of yoga, meditation, and modern wellness culture. This wave of consumption is pushing the global incense market toward the $5 billion mark in less than a decade. If Vietnam is the world's largest exporter of incense sticks, once accounting for nearly 90% of India's imports at its peak, then India remains the largest producer and consumer of incense on the planet. Each year, the country produces hundreds of thousands of tons of incense and provides employment for more than 2 million workers, most of them women in rural communities. Many people assume incense is merely a cheap, everyday item. But that perception quickly changes when Chiara is mentioned, the most expensive form of agarwood in the world, which can reach prices of up to 15,000 USD per kilogram, sometimes exceeding the value of pure gold. However, Chiara is almost a miracle of nature. It forms only when centuries-old agarwood trees become infected by specific fungi over extremely long periods, with an estimated natural occurrence rate of just 1 in a million. So how are the incense sticks that are lit every day in millions of homes and temples actually made? Let's begin the journey to uncover how incense is produced, the part we have all been waiting for. In Vietnam, around 80 to 100 traditional incense-making villages are still operating across the country, forming a vast production network that supplies billions of incense sticks to the global market every year. In the craft village of Lê Minh Xuân, considered one of the largest incense-producing hubs in the country, a single worker can produce up to 130,000 incense sticks per day. A remarkable scale for a traditional craft that has existed for centuries. Every incense stick begins with one of Asia's most familiar natural materials, bamboo. In Vietnam, the bamboo selected for incense production is typically between 3 and 5 years old, the stage at which the fiber structure has fully stabilized. At this point, the bamboo is strong enough to maintain the shape of the incense stick, yet still flexible enough to be split into thin cores without breaking. After harvesting, the bamboo culms are cut into sections and split lengthwise along the grain. This step requires extremely high precision, because even a slight deviation in the splitting line can cause the entire piece to crack along the grain and become unusable. From these larger bamboo sections, artisans continue splitting the material into thin strips. The strips are then bundled into large batches and transported to shaving workshops, where millions of incense cores are produced every day. Today, most production facilities rely on automatic shaving machines. Bamboo strips are fed into the machine, where ultra-thin steel blades continuously shave away the rough wood surface, transforming them into perfectly round sticks in seconds. Thanks to high-speed rotating blades, a single machine can produce around 30,000 to 40,000 sticks per hour, roughly equivalent to the output of about 20 manual workers who would otherwise have to carve each stick by hand, a process that is both labor-intensive and prone to painful bamboo splinters. After shaping, the sticks pass through a polishing machine where fine grinding wheels remove any remaining wood fibers. The result is a smooth and uniform surface, a crucial condition for allowing the incense powder to firmly adhere to the bamboo core later in the process. However, even after shaving, bamboo sticks still retain a certain amount of natural moisture within the wood. For this reason, they must be dried under the sun for about 1 to 2 days to completely release the remaining moisture. If the sticks do not reach the proper dryness level, the finished incense may burn unevenly or extinguish halfway through, a technical flaw considered unacceptable in many spiritual rituals. After being completely dried, the bamboo sticks move to the stage that gives incense its familiar appearance, dyeing the base of the sticks. Thousands of sticks are tightly bundled together and dipped into tanks of red or lotus pink dye. Only the bottom 4 to 6 centimeters of each stick, out of a total length of nearly 40 centimeters, are colored, creating a clear visual marker without affecting the upper section that will later be coated with incense powder. The dye solution is made by dissolving pigments in water with a small amount of adhesive, allowing the color to firmly bond to the bamboo fibers and retain its shade even after days of sun drying or long-distance transportation. In many craft villages, this task is often carried out by men, as each bundle can weigh 4 to 5 kilograms and must be repeatedly dipped and swung to ensure the dye penetrates evenly between thousands of sticks. Beyond its technical purpose, the colored base also carries cultural meaning. Lotus pink recalls Vietnam's national flower, while red symbolizes luck and sincerity in spiritual rituals and ancestral worship. After dyeing, the bundles of bamboo sticks are brought out to the yard and spread into large circular patterns, a familiar sight in many incense-making villages. At first glance, the arrangement looks like a vibrant decorative display, but it is actually a crucial drying technique. Each circle can hold about 3,000 to 5,000 sticks, arranged radially from the center so sunlight can reach the entire bundle at once. The gaps between the sticks allow air to circulate freely around each bamboo core, helping the dye dry quickly and evenly, while preventing warping or deformation after coloring. For this reason, incense production depends heavily on weather conditions. With strong sunlight, the sticks can dry in just 1 day. But during cloudy or rainy weather, the process may take 3 to 4 days, requiring workers to frequently turn the sticks to prevent moisture buildup and ensure the color dries evenly. But before bamboo sticks can become finished incense, another crucial component must be prepared: incense powder, the element that determines the fragrance of the stick. This powder is usually brown or golden brown, made from finely ground aromatic wood, blended with natural herbs. For the domestic market, the mixture is sometimes enriched with ingredients such as cinnamon, star anise, and various medicinal herbs. In some traditional recipes, it may even include up to 18 types of herbal ingredients, creating the warm and distinctive fragrance commonly associated with traditional incense. At this stage, the process moves to its most crucial step: rolling the incense, where the bamboo sticks and incense powder combine to form the finished shape of each stick. Workers pour the powder into the machine's tray and feed bundles of bamboo sticks into the rotating system. As the machine operates, the base of each stick is held firmly while the body spins and rolls through the powder. Through this rotation and gentle pressure, the powder gradually adheres to the stick, forming an even coating. Within just a few seconds, the smooth bamboo sticks become finished incense sticks, with a powder layer about 1.5 to 2 millimeters thick and a length of 35 to 40 centimeters, a familiar size in many Asian households and temples. This simple mechanism has dramatically increased productivity. While manual methods once allowed a worker to roll only about 500 sticks per day, machine-assisted production can reach up to 50,000 sticks in the same time. The incense sticks that come out of the machine are still slightly moist, so they must undergo a final drying stage until the incense powder is completely dry and firmly bonded to the bamboo core. Once they reach the required dryness, the sticks are bundled into dozens or larger batches and moved to the packaging stage. In many modern workshops, each bundle is also labeled with a barcode for traceability, completing the final step that transforms a traditional craft product into a standardized commercial good, ready to leave the workshop and release its fragrance in temples or on ancestral altars during important occasions. Unlike in Vietnam, where incense sticks are made from a bamboo core coated with aromatic powder, in Japan, the entire stick is pressed directly from incense materials with no core at all. Ingredients such as sandalwood, cinnamon, clove, and agarwood are ground into a fine powder of about 20 to 50 microns, then mixed with taboo powder, a natural binder extracted from the bark of the mochilas tree. In traditional formulas, taboo typically makes up about 10% of the mixture, providing enough binding strength while preserving the natural aroma of the woods. After being measured in precise proportions, the entire mixture is transferred into a large mixing tank. Here, 2 heavy grinding wheels rotate slowly, continuously pressing, kneading, and blending the powder with water until the material reaches a clay-like consistency. This process typically lasts 30 to 60 minutes, allowing water to penetrate evenly into every particle, while the moisture level is maintained at around 25%. An ideal balance that ensures the mixture is cohesive enough to bind together, yet soft enough to pass through the extrusion mold. Because it is made entirely from natural aromatic wood powder, Japanese-style incense sticks usually develop a distinct brown or dark brown color after shaping, unlike the bright red base commonly seen in bamboo core incense across many parts of Asia. In some modern production lines, the mixture may also be given a light blue tint to help differentiate fragrance formulas and facilitate process control before being extruded into the coreless incense sticks characteristic of Japan. When the mixture reaches its ideal pliable consistency, the process moves to the most critical stage, incense extrusion. The material is fed into a hydraulic press fitted with a metal die plate containing about 200 to 300 tiny holes, each forming one incense stick. As the piston compresses, the entire mass is pushed through the die simultaneously, quickly producing hundreds of thin, straight incense strands. Unlike Vietnamese incense, which relies on a bamboo core to maintain its shape, Japanese incense must hold its structure entirely through the body of the incense itself. For this reason, parameters such as the diameter of the die holes, piston pressure, and the fineness and moisture content of the mixture must be precisely controlled. Through this mechanism, a single batch of paste can produce 200 to 300 incense sticks at once, each about 2 to 3 millimeters thick, yet still straight and strong enough for the next stages of production. Immediately after leaving the extrusion mold, the incense strands are still very soft, almost like pliable clay, making them easy to bend or break if separated individually. For this reason, they are kept together as a single sheet and laid flat to stabilize the structure, allowing pressure to distribute evenly across the surface and minimizing deformation. Once the surface begins to firm up, artisans use a sharp circular blade that rolls along a guiding rail to cut the sheet. Thanks to the blade's rolling motion, The cutting force is directed downward rather than sideways, allowing the entire sheet of incense to be sliced cleanly in a single pass with almost no displacement of the strands. Using this method, hundreds of incense sticks can be cut simultaneously to a standard length of about 13 to 15 centimeters, with a tolerance of less than 1 millimeter. The level of precision needed to ensure the sticks burn steadily and evenly during use. However, even after reaching their final size, the incense bodies are still not fully stable. The remaining moisture in the mixture requires them to undergo a drying stage before packaging. The sheets of incense are placed on multi-tier wooden racks, where each strand is kept straight and stable in an environment of around 25 degrees Celsius for up to 48 hours. With continuous air circulation, moisture gradually evaporates from the incense body, allowing the structure of the aromatic powder to shrink evenly, a key factor that enables each stick to burn steadily for about 20 to 30 minutes, depending on its length. Finally, once the incense sticks are completely dry, workers gather them into small bundles and carefully align them by hand so that the sticks lie perfectly parallel. Each bundle typically contains 30 to 50 sticks and is secured with a thin strip of paper wrapped around the middle to maintain the structure and protect the incense surface during transportation. The bundles then undergo a final inspection, where any sticks that are bent, broken, or uneven in color are removed before being packed into tubes or paper boxes decorated with traditional patterns. A finished bundle of Japanese incense is characterized by perfectly straight sticks, flat cut ends, and nearly uniform color. This precision reflects the distinctive craftsmanship philosophy of Japanese incense making, where a high-quality box of incense may cost $20 to $100, offering in return a clean, delicate stream of smoke, a long and tidy ash line, and a fragrance that spreads softly and deeply without being harsh or heavy. More than 13 million tons of animal hides are harvested worldwide each year, becoming a core raw material for fashion, furniture, automobiles, and high-end accessories, powering a market worth around $450 billion. Behind it lies a system operating like a global machine. Tanneries compete with processing technologies precise down to thousandths of a millimeter, while Asia, Europe, and Latin America vie for million-dollar contracts. In this video, join us as we uncover the transformative journey of a material once dismissed as a low-value byproduct, and how it has risen to become one of the most economically significant materials today. Nicknamed the king of the global meat industry, beef cattle hide, the part least talked about, accounts for up to 15% of the total economic value of each animal. Its rebirth begins with tons of raw hides separated from the carcass, still moist, still fatty, still carrying tissue residues. Before reaching this point, modern skinning techniques in processing plants preserve nearly the entire surface area of the hide, leaving only a thin layer of flesh attached. At the processing facility, high-pressure water jets are sprayed evenly across the hide to wash away all impurities while bringing its moisture level back to balance, helping limit shrinkage during the deeper treatment stages. From here, the soaking drums, massive steel cylinders holding water 2 to 3 times the weight of the hides, initiate the first transformation. The drum rotates slowly, creating a continuous circulation that allows water and mild chemical agents to penetrate the fiber network, causing the hide to expand from the inside out. This expansion naturally loosens the hair from its keratin structure without heavy abrasion, exposing a clean, raw surface ready for the fleshing machine to remove any remaining fat and tissue and bring the hide to a uniform thickness before tanning. Next comes the most critical stage, chrome tanning. Inside the chrome drum, trivalent chromium ions, chrome 3, bond with collagen, locking the fiber network in place and compressing the entire stabilization process into less than 2 days. The result is wet blue, a semi-finished hide with its signature blue tint created by chromium complexes. Immediately after, retanning and dyeing continue to push color deep into each collagen fiber, giving premium leather its softness, durability, and exceptional abrasion resistance. Few people know that raw cattle hides are among the United States' strongest agricultural export commodities, surpassing even cotton and fresh pork, products traditionally regarded as cornerstones of American agricultural exports. No longer limited to wool, sheepskin is emerging as a new value driver, pushing the global shearling industry past $25 billion per year. In semi-arid livestock regions like Australia, the shearling hub of the southern hemisphere, sheep are raised on fiber-rich pasture, supplemented with hay, grains, and trace minerals to stabilize wool fibers and skin quality. However, once value shifts toward the hide, two risks become critical: parasites that damage hair follicles and abnormal moisture that causes dirt accumulation, both of which can slash the value of shearling by up to half right at the farm. When processing begins, the carcass is suspended on an overhead rail and fed into a rotary de-hiding machine, where mechanical clamps secure the body as the rotating drum applies consistent pulling force. By controlling tension and speed, the hide is removed in one continuous sheet, minimizing cut lines and preserving the integrity of the collagen layer, along with the fine wool. From this point on, these intact pelts become the central focus of the tanning process, where raw hide still carrying traces of blood, capillaries, and thin flesh must be completely removed in the drum, without disturbing even the microscopic structure of the hair roots. Unlike cattle hides, which have dense collagen and high mechanical resistance, sheepskin is thin and rich in lanolin, requiring the entire tanning process to operate at lower pH, gentler mechanical action, and in a much narrower temperature range. A tiny deviation can trigger collagen shrinkage, surface discoloration, or wool collapse, the very reasons premium shearling can be up to 3 times more expensive than smooth leather. After tanning, the natural wool, prone to uneven curl and inconsistent distribution, must go through a specialized wool finishing machine. Using a slow-rotating pressing roller combined with a gentle stream of warm air, the machine straightens, fluffs, and equalizes wool density, creating the thick, smooth, resilient surface that defines luxury shearling. What many people don't know is that a high-grade sheepskin can increase human body warmth by up to 12% in cold environments. But in return, every finished shearling pelt consumes up to 70 liters of water and generates nearly 1 kilogram of solid tanning waste, raising enormous questions behind the comfort it delivers. In Southeast Asia, the region supplying most of the world's python skins to the European market, each hide represents the culmination of an entire life cycle, earned through the constant risks faced by those who raise these reptiles that can grow several meters long. Python farms are built with thick walls, steel-locked doors, and individual enclosures. Every gap must be under 1 to 2 centimeters, because anything wider allows a python to slip through and escape with constricting force that is extremely difficult to control. Their diet consists of rats, rabbits, or small poultry, fed every 5 to 7 days to maintain steady growth and preserve the pigmentation on each diamond-shaped scale, the key factor determining the value of the hide. Stress or malnutrition can dull the pattern, drastically reducing its commercial worth right at the farm. After 12 to 18 months, when size and pattern reach their prime, the snake is anesthetized for processing. Because python skin forms a large tubular structure, the removal begins with a straight incision along the belly. The rest is peeled by hand, slowly and evenly, to preserve the signature scale zones, especially the dorsal section, which defines the luxury tier. The skin is then washed, degreased, and lightly tanned for several hours to stabilize the collagen without blurring the microscopic pattern, something synthetic materials still cannot replicate perfectly today. Yet only about 10 to 15% of python skins meet premium grade standards, despite the enormous risk and labor involved. This uniqueness, no two hides ever share the same pattern, combined with limited supply keeps python leather priced far above many conventional hides in the world of luxury fashion.